Good morning, students. Today we discuss homogeneous linear equation. It's a part of third unit. We have already discussed differential equation with constant coefficient. In this homogeneous equation, we convert homogeneous equation into a differential equation with constant coefficient. Here, equation number 1 shows the standard form or general form of homogeneous differential equation or homogeneous linear differential equation. The important thing or the thing how we can recognize a given equation is of homogeneous type. The index of x or the power of x must be equal to order of its derivative. Here in first term, power of x is n, and similarly order of derivative is n, and in second term power of x is n minus 1 and order of derivative is n minus 1, and so on. So its general form is x raised to power n d raised to power n plus a1 x raised to power n minus 1 d n minus 1 plus so on a n y is equals to some function of x. Here a1, a2, a n are some real constant, and the right hand part phi is some function of x. Many times homogeneous equations are also called as Cauchy-Euler equation. Now we'll look how we solve such type of equation. In this equation, generally we assume x is equals to exponential z. That is, what we do, we just convert independent variable into some another independent variable. Here x is an independent variable, and we convert x into some another independent variable, that is z, with the relation x is equals to exponential z, or we can say z is equals to log of x. If we differentiate it with respect to x both sides, we get dz upon dx is equals to 1 upon x. In equation, our dependent variable is y and independent variable is x, and we have already converted x into z, so we are to find derivative of y with respect to z. So dy upon dx can be expressed as dy upon dz into dz upon dx by chain rule, and as we know dz upon dx is equals to 1 upon x, so dy upon dx can be written as 1 upon x dy upon dz. Or if we simplify this equation, we get x dy upon dx is equals to dy upon dz. Or we can say it x d is equals to d dash, where d stands for d by dx, whereas d dash stands for d by dz. Similarly, we try to find d2y upon dx square, that is second order derivative of y with respect to x. We have already calculated dy upon dx, which is given by 1 upon x dy upon dz. Now differentiate 1 by x dy upon dz with respect to x to get d2y upon dx square, and this is given by minus 1 by x square dy upon dz plus 1 by x d by dx of dy by dz. Now when we simplify this equation using chain rule, we get second term converts into 1 by x d by dz of d by dz into dz by dx. After simplifying this or putting the value of dz upon dx is 1 by x, we get d2y upon dx square is equals to minus 1 by x square dy by dz plus 1 by x square d2y upon dz square. Taking 1 upon x square outside from right hand side and simplifying it, we get x square d square is equals to d dash square minus d dash, or x square d square is equals to d dash minus 1. Here again d stands for d by dx and d dash stands for d by dz. Similarly, we can find x cube d cube, which can be written as d dash minus 1, d dash minus 2, and so on. We put all these terms in equation number 1, and it becomes a linear differential equation with constant coefficient. and we know how can we solve a differential equation with the constant coefficient, a linear differential equation with constant coefficient. We have already studied in previous lectures. Here, an important thing in a differential equation with constant coefficient, when we solve, its complementary function can be written as exponential m1z type. Here, z is equals to log x. So, it converts into exponential log x raised to power m. And finally, it converts into x raised to power m1. So, here we discuss different cases when the roots of auxiliary equation are m1, m2, mn. In that case, we can write CF. If given m1 or roots m1, m2, mn are real and distinct, in that case, CF can be written as C1 x raised to power m1 plus C2 x raised to power m2 and so on. If roots are real and repeated, in that case, if suppose m1 and m2 are same, say m, then CF is C1 plus C2 log x raised to power m plus so on. And if roots are imaginary, CF can be given by x raised to power alpha, C1 cos beta log x plus C2 sin beta log x. Now, we look some example. Here we are given with a problem x square d square plus 3x d plus 1 y is equals to 1 upon 1 minus x raised to power 2. Look here, in every term, index of x same as the order of derivative. So, the given equation is an homogeneous equation. Very first, we convert x into z using the relation z is equals to log x or x is equals to exponential z. When we convert x into z, given equation convert into d dash minus 1 plus 3d dash plus 1 y is equals to 1 upon 1 minus exponential z raised to power 2. Here d dash is what? D by dz. When we simplify this, we get d dash square plus 2d dash plus 1 y is equals to 1 upon 1 minus exponential z raised to power 2. Now, here equation 1 is just like a differential equation with constant coefficient. Its auxiliary equation given by m square plus 2m plus 1 is equals to 0 and its root are m is equals to minus 1 minus 1. Here roots are real and same repeated. So, CF is given by C1 plus C2 log x into 1 upon x. Now, to find Pi, we calculate 1 upon d dash plus 1 raised to power 2 of 1 upon 1 minus exponential z square. Now, using general process, we find particular integral. As we calculate Pi in differential equation with constant coefficient, we convert, first we write 1 upon d dash plus 1 whole square is equals to 1 upon d dash plus 1 and 1 upon d dash plus 1. And we calculate Pi of 1 upon 1 minus exponential z square with respect to 1 upon d dash plus 1. After calculating this, again we calculate the result, we calculate Pi of resulted with respect to 1 upon d dash plus 1. And here we apply the formula 1 upon d minus alpha of phi x is equals to exponential alpha integration of exponential minus alpha phi x dx. Similarly, it converts into, or using this formula, it converts into 1 upon d dash plus 1 exponential minus z integration of exponential z 1 upon 1 minus exponential z square dz. Now, to solve this integration, first we assume exponential z is equals to t and replace into integration. We find integration 1 upon 1 minus t whole square dt. Now, when we integrate this term, we find exponential minus z 1 upon 1 minus t and t is what? Exponential z. So again replace t with respect to exponential z. We get exponential minus z into 1 upon 1 minus exponential z. Now find pi of exponential minus z into 1 upon 1 minus exponential z with respect to d dash plus 1. So again using general formula exponential minus alpha integration exponential alpha phi x dx, we get exponential minus z integration of exponential z exponential minus z upon 1 minus exponential z dz. Again to solve it, we assume exponential z is equals to t, and when we solve this integration we find the final result like exponential minus z log t minus log 1 minus t, or when we replace t with exponential z back, we get exponential minus z log exponential z upon 1 minus exponential z. Here exponential z is equals to x, so pi can be written as pi is equals to x inverse log x upon 1 minus x. Hence the complete solution is given by y is equals to cf plus pi, and cf is c1 plus c2 log x inverse, and pi is x inverse log x upon 1 minus x. So y is c1 plus c2 log x inverse plus x inverse log x upon 1 minus x. Now look, another problem. 3x plus 2 whole square d square plus 3x plus 2d minus 36y is equals to 3x square plus 4x plus 1. To solve such type of problem, first we write given equation into standard homogeneous form. To convert it into standard homogeneous form, we replace 3x plus 2 by v. We get d is equals to d by dv into 3, or 3d by dv is equals to capital D, where d is d by dx. So using this transformation 3x plus 2 is equals to v, our problem convert into 3 square v square d2y upon dv square plus 9v 3 into 3v dy upon dv minus 36y is equals to 3 v minus 2 upon 3 square plus 4 v minus 2 by 3 plus 1, or it can be written as given in equation number 2, v square d square plus vd minus 4y is equals to 1 upon 27 v square minus 1. Here equation 2 is standard homogeneous equation. In first term, index of v is just similar as the order of derivative, which is 2. In second term, index of v is exactly same as order of derivative, which is 1. Now taking z is equals to log v is equals to exponential z. Using this transformation given equation number 2 convert into a differential equation with constant coefficient. Taking v is equals to exponential z, we get d dash square minus 4y is equals to 1 upon 27 exponential 2z minus 1. Now we can solve it using CF and PI. The auxiliary equation of equation 3 is m square minus 4 is equals to 0. When we solve it, we get m is equals to plus minus 2, and CF is given by c1v square plus c2v raised to power minus 2, where v is what? 3x plus 2. So finally c1 can be written as c1 3x plus 2 whole square plus c2 3x plus 2 whole power minus 2. Now to calculate pi, we solve 1 upon d dash square minus 4 of exponential 2z minus 1 upon 27. We separate these two terms, exponential 2z upon 27 and 1 upon 27, and separately we calculate pi for each term. For first term, if we replace d dash with 2, denominator becomes 0. So first we write its fraction d dash minus 2 and d dash plus 2. Here first fraction becomes 0 due to d dash is equals to 2. So pi can be written as z by 4 exponential 2z. And for second term, pi is just 1 by 4. So finally pi is what? 1 by 27 into z by 4 exponential 2z plus 1 by 4. When we solve this, we get 1 upon 108 into z exponential 2z plus 1. Or now here we replace z. We get 1 upon 108 log 3x plus 2. Z is log v and v is 3x plus 2. So it becomes 1 upon 108 log 3x plus 2 exponential 2 log 3x plus 2 plus 1. Or we can write complete solution by this equation: y is equals to c1 3x plus 2 whole power 2 plus c2 3x plus 2 whole power minus 2 plus 1 upon 108 into 3x plus 2 whole square log of 3x plus 2 plus 1. Okay, that's all. Here are some problems to solve by you. Thank you.